William Shockley slammed the lab report onto his desk, hard enough that the other researchers in the Palo Alto building looked up from their oscilloscopes. It was October 1958, and one of his engineers had just told him that silicon, not germanium, should be the future of semiconductor manufacturing. Shockley had co-invented the transistor 11 years earlier at Bell Labs in New Jersey, sharing a Nobel Prize for the breakthrough that replaced vacuum tubes with solid-state electronics. He'd built his California startup, Shockley Semiconductor Laboratory, on germanium expertise. And now this engineer, barely 30 years old, was suggesting they abandon everything. The engineer's name was Jean Hoerni, a Swiss-born physicist with a doctorate from Cambridge who joined Shockley's team in 1956. Hoerni had been running thermal tests on germanium transistors, pushing them through temperature cycles that simulated real-world military conditions. The results were damning. Above 85 degrees Fahrenheit, germanium's crystalline structure started leaking electrons like a sieve. The transistors didn't fail catastrophically. They just became unreliable, their amplification dropping unpredictably. For a radio in someone's living room, this was annoying. For a guidance system in a nuclear missile, it was unacceptable. Shockley refused to listen. Germanium had been perfected over a decade of research at Bell Labs. The manufacturing processes were established, the crystal growing techniques refined, the doping procedures documented in hundreds of lab notebooks. Silicon, by contrast, required furnace temperatures above 2,600 degrees Fahrenheit, nearly double what germanium needed. The slightest contamination would ruin an entire batch. Shockley told Hoerni to focus on improving germanium rather than chasing silicon fantasies. The argument escalated over 3 weeks. Hoerni brought data showing that silicon's electron mobility remained stable up to 300 degrees Fahrenheit. Shockley countered that nobody could manufacture silicon transistors reliably at scale. Other engineers began taking sides. The laboratory, which had started with such promise just 2 years earlier, fractured into factions. By November, the situation had become untenable. Shockley called Hoerni into his office and made it clear: work on germanium or leave. Hoerni chose to leave. He wasn't alone. 7 other engineers walked out with him, including Gordon Moore and Robert Noyce, men who would go on to found Intel and revolutionize computing. The press called them the traitorous 8, but they had something Shockley didn't: a conviction that silicon was the only path forward for semiconductor electronics that could survive real-world conditions. Hoerni moved to a small facility in Mountain View, backed by Fairchild Camera and Instrument Corporation. He set up furnaces capable of reaching silicon's melting point, installed clean rooms with filtered air to prevent contamination, and began experimenting with silicon wafer production. The military had started circulating requests for proposals. They needed transistors that could function reliably in missiles, in aircraft, in satellites exposed to temperature extremes. Germanium couldn't do it. Vacuum tubes were too fragile. Silicon was the only answer if anyone could figure out how to manufacture it. Shockley Semiconductor would never produce a commercially successful product. The company that fired its best engineers over a technical disagreement faded into obscurity. But Hoerni's obsession with silicon would solve the most critical electronics challenge of the Cold War, enabling weapon systems that gave the United States an insurmountable technological advantage over the Soviet Union. The transistor's debut on June 30th, 1947, at Bell Labs in Murray Hill, New Jersey, should have changed everything immediately. John Bardeen and Walter Brattain had spent months working with germanium crystals, trying to understand how electrons moved through semiconductors. They'd built a device using 2 gold contacts pressed against a germanium crystal mounted on a metal base, the whole assembly no larger than a pencil eraser. When they applied voltage, the tiny device amplified electrical signals just like a vacuum tube, but without the heat, without the fragile glass envelope, without the glowing filament that burned out after a few thousand hours. Bell Labs held a press conference, and the technical demonstrations were flawless. A transistor radio worked perfectly, consuming a fraction of the power that vacuum tube radios required. The device operated at room temperature, turned on instantly without warm-up time, and could theoretically last indefinitely since it had no filament to burn out. The Bell Labs researchers presented calculations showing that transistors could be manufactured smaller than vacuum tubes, potentially enabling portable electronics that didn't exist yet. The military representatives who attended took notes, asked polite questions, and returned to Washington unimpressed. The Army Signal Corps had just spent millions developing improved vacuum tube designs for battlefield radios. The Navy had entire supply chains built around vacuum tube specifications. The Air Force was designing bomber electronics around tube-based systems that engineers understood thoroughly. Germanium transistors were laboratory curiosities, interesting physics experiments that might have commercial applications someday, but not serious replacements for proven military hardware. The problem wasn't performance in controlled environments. In Bell Labs, with temperature regulation and careful handling, germanium transistors worked beautifully. But military equipment operated in conditions that laboratory researchers rarely considered. Aircraft electronics experienced temperature swings from -65 degrees at altitude to 160 degrees on desert runways. Naval equipment faced humidity that corroded contacts and salt air that degraded components. Battlefield radios got dropped, submerged, and operated continuously for days without maintenance. Vacuum tubes had been tested under all these conditions for 30 years. Engineers knew exactly how they failed, how to design redundancy, how to calculate mean time between failures. Transistors were unknown quantities. The military procurement officers wanted data, not from laboratory benches, but from field tests under combat conditions. They wanted reliability studies, failure analysis, manufacturing consistency reports. Bell Labs had none of that in 1947. Western Electric, Bell's manufacturing division, began producing germanium transistors for hearing aids in 1952. The devices worked well in that application. They operated at body temperature in controlled environments, and the small size enabled hearing aids that could fit behind a person's ear instead of requiring a separate battery pack. Texas Instruments started manufacturing transistor radios in 1954, selling them commercially for $49. Consumers loved them. The devices were portable, battery-powered, and reliable enough for entertainment purposes. But the military wanted more than entertainment-grade reliability. They were developing weapon systems that would sit in missile silos for years, ready to launch within minutes. They were building aircraft that would fly through temperature extremes while depending on electronic navigation. They were designing submarines that would operate underwater for months with no possibility of repairs. For these applications, germanium transistors in 1954 were still unproven technology. Then the Korean War provided the field test that Bell Labs never conducted. Soldiers carried transistor radios into combat, and the devices began failing in ways that laboratory testing hadn't predicted. The failures weren't random. They followed a pattern that pointed to a fundamental flaw in germanium's crystalline structure. The field reports from Korea started arriving at Bell Labs in late 1952, and the pattern was unmistakable. Transistor radios that worked perfectly during morning operations would become unreliable by afternoon. Signal amplification would drop by 30 or 40% as temperatures climbed above 85 degrees Fahrenheit. By the time ambient temperature reached 95 degrees, common in Korean summers, the transistors were essentially useless. Soldiers reported that radios would recover functionality at night when temperatures dropped, only to fail again the next day. This wasn't battle damage or manufacturing defects. It was something intrinsic to germanium itself. Bell Labs researchers ran systematic temperature tests through 1953, and the physics became clear. Germanium has a narrow band gap. The energy difference between electrons bound to atoms and electrons free to conduct electricity. At room temperature, this band gap measures 0.67 electron volts, which provides adequate separation between bound and free electrons. But as temperature increases, thermal energy begins exciting electrons across that gap spontaneously. By 85 degrees Fahrenheit, enough electrons are jumping the gap that germanium starts conducting current, even without applied voltage, a phenomenon called thermal runaway. The problem compounded itself. As unintended current flowed through the transistor, it generated heat, which excited more electrons, which generated more heat. In extreme cases, germanium transistors would literally cook themselves into permanent failure. Even when they didn't fail catastrophically, their behavior became unpredictable. Amplification factors would drift, threshold voltages would shift, and timing circuits would fall out of specification. Equipment that depended on precise transistor characteristics simply stopped working reliably. Texas Instruments tried compensating with elaborate cooling systems, adding heat sinks, and forced air circulation to transistor assemblies. This worked in laboratory conditions, but added weight, complexity, and power consumption that defeated the original advantages of solid-state electronics. The military needed electronics that worked without auxiliary cooling systems, that functioned reliably across the full temperature range from Arctic cold to desert heat. Germanium couldn't deliver that performance. By 1954, the semiconductor industry faced a fundamental choice. Researchers could continue refining germanium processes, hoping to find alloys or doping techniques that would extend the usable temperature range, or they could abandon a decade of germanium expertise and start over with silicon, an element that had a band gap of 1.12 electron volts, wide enough to prevent thermal runaway up to 300 degrees Fahrenheit. Silicon's thermal stability was undeniable, but every other characteristic made it harder to work with than germanium. Silicon melts at 2,577 degrees Fahrenheit compared to germanium's 1,720 degrees. Growing pure silicon crystals required furnaces that could maintain temperatures within 5 degrees across a chamber the size of a basketball. The slightest contamination, a microscopic particle of dust, a trace of oxygen, a fingerprint on a wafer, would introduce impurities that destroyed the crystalline structure. Germanium tolerated small imperfections. Silicon did not. Cutting silicon into wafers was equally challenging. The material was harder and more brittle than germanium, shattering under the diamond saws used for germanium production. Polishing silicon wafers to the mirror-smooth surface required for transistor manufacturing took hours of careful work. Manufacturing yields were abysmal. Researchers would start with 10 silicon wafers and end up with 1 or 2 that met specifications. The Korean War transistor failures made the choice unavoidable. Germanium's temperature limitations weren't engineering problems that could be solved through refinement. They were physics limitations imposed by the element's atomic structure. If the military wanted reliable solid-state electronics for weapon systems, the semiconductor industry would have to master silicon manufacturing. The first silicon transistor emerged from Bell Labs in 1954, and it took Morris Tannenbaum 6 months of failed attempts to produce it. The process began with growing a silicon crystal from molten material heated to 2,600 degrees Fahrenheit in a quartz crucible. Tannenbaum would lower a seed crystal into the melt and slowly pull it upward, rotating it at precise speeds while maintaining temperature uniformity across the entire furnace. A single temperature fluctuation would introduce crystal defects that propagated through the entire ingot, rendering it useless. When he successfully grew a crystal, perhaps 1 attempt in 5, the next challenge was sawing it into wafers without shattering the brittle silicon. Diamond-tipped saws would bind in the cut, generating heat that caused the crystal to crack along cleavage planes. Tannenbaum experimented with cutting speeds, blade thickness, and cooling methods. Most crystals broke during slicing. Those that survived had to be polished to optical flatness, with surface roughness measured in nanometers. A scratch invisible to the naked eye would create defects where transistors were fabricated. The cleanroom requirements pushed beyond anything the semiconductor industry had attempted. A single dust particle landing on a silicon wafer during processing would create a contamination site where impurities would concentrate. Bell Labs installed air filtration systems that removed particles down to 0.3 microns, but workers themselves were contamination sources. Skin cells, hair, lint from clothing, all of it had to be controlled. Technicians wore full-body suits, gloves, and face masks. They entered the fabrication area through airlocks, where high-velocity air blew away loose particles. Even in these controlled conditions, doping silicon with precise impurity concentrations remained more art than science in 1955. Transistors require carefully controlled regions of different conductivity types. N-type, where phosphorus atoms donate electrons. P-type, where boron atoms accept electrons. With germanium, researchers could diffuse impurities at 900 degrees for predictable results. Silicon required diffusion at 1900 degrees, where everything happened faster, and controlling the depth of impurity penetration became exponentially more difficult. Gordon Teal at Texas Instruments was growing silicon crystals, using a process where he pulled the crystal from the melt while introducing controlled amounts of dopant gases. The technique worked, but yields were terrible. He'd produce a silicon ingot 6 inches long, slice it into 30 wafers, and discover that only 3 or 4 had uniform doping. The rest would have concentration gradients, crystal defects, or contamination that made them unsuitable for transistor fabrication. At $10 per wafer for materials and labor, every failure was expensive. By 1957, Bell Labs had established a silicon transistor production line that could manufacture devices with 25% yield, meaning 3 out of 4 attempts resulted in scrap. This was actually considered progress. The transistors that did work showed remarkable thermal stability, continuing to function reliably at temperatures where germanium devices would have failed completely. But the manufacturing challenges made silicon transistors cost 20 times more than germanium equivalents. The military was willing to pay that premium for weapon systems where reliability mattered more than cost, but only if someone could scale up production. Making a few dozen silicon transistors per month in a laboratory was very different from manufacturing thousands per week for missile guidance systems. The process needed fundamental breakthroughs that would allow mass production with consistent quality. The techniques that worked for small-batch laboratory fabrication simply wouldn't scale. That's when Gene Hoerni, now working at Fairchild Semiconductor after leaving Shockley, started experimenting with silicon oxide layers. He wasn't trying to improve yields or reduce costs. He was trying to solve a completely different problem, but his solution would transform silicon from an expensive laboratory material into the foundation of modern electronics. Gene Hoerni's laboratory at Fairchild Semiconductor in Mountain View looked like a disaster by early 1959. Silicon wafers with failed experiments covered his workbench, each one representing hours of furnace time and careful processing that ended in transistors that didn't work properly. The problem wasn't thermal stability. Silicon handled temperature extremes perfectly. The problem was that every time Hoerni tried to create multiple transistors on a single wafer, the process of making electrical connections to them damaged the delicate semiconductor junctions underneath. The standard method involved diffusing impurities into silicon to create the transistor structure, then etching away material to expose the junctions where wire connections would attach. But etching was violent chemistry, hydrofluoric acid dissolving silicon, leaving rough surfaces that accumulated contaminants. Every exposed junction became a potential failure point. Moisture could penetrate, impurities could migrate, and the carefully engineered electrical properties would degrade over time. For military applications requiring decades of shelf life, this was unacceptable. Hoerni had been watching silicon wafers oxidize naturally in air after high-temperature processing. Silicon dioxide, essentially glass, would form a thin layer on the surface, and this oxide layer was remarkably stable. It didn't conduct electricity, it resisted chemical attack, and it adhered to the silicon beneath it with almost molecular perfection. In February 1959, Hoerni realized the oxide layer wasn't contamination to be removed. It was protection to be exploited. He developed what he called the planar process. Instead of etching away material to expose junctions, he would grow a silicon dioxide layer across the entire wafer surface, then selectively remove oxide only where he needed to make electrical contact. The oxide would remain in place over the actual transistor junctions, sealing them permanently against contamination. He could diffuse impurities through windows opened in the oxide, creating transistor structures that were protected from the moment they were formed. The technique required developing photolithography methods borrowed from the printing industry. Hoerni would coat an oxidized silicon wafer with light-sensitive resist, expose it through a photographic mask that defined the pattern of windows, then develop the resist-like film in a darkroom. Acid would etch through the oxide only where the resist had been removed, leaving precise patterns that could be reproduced identically across hundreds of transistors on a single wafer. By June 1959, Hoerni was producing silicon transistors with oxide passivation that showed stability far beyond anything the industry had achieved. He sealed transistors in packages and subjected them to accelerated aging tests, high temperature, high humidity, thermal cycling that simulated years of environmental exposure compressed into weeks. The planar transistors showed essentially no degradation. Their electrical characteristics remained within specification through temperature cycles from -65 to 300 degrees Fahrenheit. The manufacturing implications were profound. With the planar process, Hoerni could fabricate dozens of transistors simultaneously on a single silicon wafer, all protected by oxide layers from the moment they were created. Yields jumped from 25% to 70% almost immediately because the oxide's protection prevented the contamination that had ruined so many devices during handling and processing. More importantly, the planar approach enabled reproducibility. Transistors made on Monday performed identically to transistors made on Friday because the oxide layer enforced consistent geometry and protected against process variations. Robert Noyce, working alongside Hoerni at Fairchild, immediately saw that the planar process solved another problem entirely. If transistors were sitting on a flat oxidized surface with their junctions protected, why connect them with individual wires? Noyce proposed depositing metal patterns directly onto the oxide layer, creating interconnections that would link multiple transistors into complete circuits. This was the birth of the integrated circuit. But the military didn't care about that yet. They cared about reliable transistors for missiles. The Air Force issued Request for Proposal AF-33 in March 1960, and the specifications were brutal. The Minuteman intercontinental ballistic missile program needed guidance computers that could survive silo storage at -65 degrees Fahrenheit, launch acceleration of 100 g-forces, and operation in the vacuum of space, where temperatures would swing from -100 to +160 degrees as the missile rotated through sunlight and shadow. Each guidance system required approximately 2,000 transistors working in concert to calculate trajectory corrections, process gyroscope data, and control the 3 stages of rocket engines. A single transistor failure would send a nuclear warhead hundreds of miles off course. Vacuum tubes were out of the question. Each Minuteman missile had to remain launch-ready for 10 years without maintenance. Vacuum tube filaments degraded even when unpowered, and the vibration during launch would shatter glass envelopes. The guidance computer alone would require 8,000 vacuum tubes given the redundancy needed for reliability, plus power supplies generating kilowatts of electricity and cooling systems to dissipate the heat. The missile didn't have room or weight budget for any of that. Germanium transistors had already failed the thermal requirements. Autonetics, the prime contractor for Minuteman guidance, had run qualification tests through 1959 using germanium-based prototypes. The transistors worked fine in temperature-controlled laboratories, but became unreliable above 85 degrees. In simulated space conditions with thermal cycling, germanium transistors would work for a few cycles, then start showing parameter drift. After 50 thermal cycles, representing perhaps a week in orbit, 30% of the transistors had failed completely. The Air Force specification called for mean time between failures of 100,000 hours and operational temperature range from -65 to +160 degrees Fahrenheit. No existing electronics met that requirement. Colonel Edward Hall, program manager for Minuteman, made it clear that if the semiconductor industry couldn't deliver reliable solid-state guidance computers, the Air Force would redesign the missile around a different guidance approach, probably inertial platforms that were heavier, less accurate, and far more expensive. Fairchild Semiconductor submitted test samples in July 1960. The transistors used Hoerni's planar process with silicon oxide passivation, fabricated on silicon wafers with carefully controlled crystal orientation and doping profiles. Each transistor was hermetically sealed in a metal can, filled with dry nitrogen to prevent any moisture contamination. Autonetics received 500 devices and began qualification testing that would run for 6 months. The tests simulated everything the guidance computer would experience. Transistors were powered continuously at maximum rated temperature for 1,000 hours, representing years of shelf life accelerated through temperature. They were thermal cycled 200 times between temperature extremes. They were vibrated at frequencies matching launch acceleration profiles. They were exposed to ionizing radiation levels equivalent to a near miss from an enemy nuclear warhead. Through all of this, the Fairchild planar silicon transistors continued functioning within specification. By December 1960, Autonetics had the data the Air Force demanded. The silicon transistors showed failure rates below 0.01% per 1,000 hours, meaning that in a guidance computer with 2,000 transistors, the probability of any single transistor failing during a 10-year service life was less than 2%. With modest redundancy designed into the computer architecture, reliability exceeded 99.8%. This was better than any electronic system ever deployed in a military application. The Air Force awarded Fairchild a production contract in January 1961 for 2 million transistors per year. At $3 per transistor, expensive but acceptable for a weapon system where each missile cost $1 million, this represented the first large-scale military procurement of silicon semiconductors. The contract specified delivery of 40,000 transistors per week starting in June 1961, with yield requirements that forced Fairchild to prove their manufacturing process was truly scalable. Fairchild's Mountain View fabrication facility ran 3 shifts, starting in March 1961, and the production numbers told a story that would reshape American strategic planning. In the first month, they produced 28,000 transistors, with 73% passing final electrical testing and environmental qualification. By June, production hit 42,000 sold per month, with yields at 81%. The planar process that Hoerni had developed for reliability turned out to enable mass production in ways that no one had anticipated. The Minuteman guidance computer, designated the D-17B, entered production at Autonetics in September 1961. The device was extraordinary for its time. A digital computer weighing 62 pounds that consumed 115 watts of power and could perform 12,190 additions per second. Every calculation ran through circuits built from discrete silicon transistors, with magnetic core memory storing the trajectory equations and targeting data. The computer would guide a missile traveling at 15,000 miles per hour through the vacuum of space, calculating course corrections every second, based on gyroscope inputs and executing commands to adjust rocket thrust vectors. The first Minuteman squadron became operational at Malmstrom Air Force Base in Montana in October 1962, just as the Cuban Missile Crisis brought the world closest it had ever come to nuclear war. 50 missiles sat in underground silos, each carrying a 1.2 megaton W-59 thermonuclear warhead and a guidance computer filled with silicon transistors that had to work perfectly on the first attempt. There would be no second chances, no maintenance crews, no replacement parts once the missiles launched. The transistors either worked or millions of people died in the wrong cities. The reliability data from operational deployment exceeded even the qualification test results. Through 1963 and 1964, as more Minuteman squadrons came online, the guidance computers logged hundreds of thousands of hours of operation in silo storage conditions. Monthly status checks showed the transistors maintaining their electrical parameters with essentially no drift. Temperature cycling from Montana winters to summer heat produced no failures. The hermetic sealing and silicon oxide passivation that Hoerni had developed kept moisture and contaminants away from the semiconductor junctions indefinitely. By 1964, when Minuteman III entered development with more sophisticated guidance requirements, Autonetics specified 6,000 transistors per missile, triple the original design. The guidance computer now included integration algorithms that processed accelerometer data to calculate velocity and position with accuracy measured in hundreds of feet over intercontinental distances. A Minuteman III, launched from Montana, could hit a target in Moscow with circular error probable of 900 feet, meaning half the warheads would land within 900 feet of the aim point after traveling 6,000 miles. Soviet missile guidance systems, by comparison, achieved circular error probable of 2 to 3 miles using vacuum tube computers that consumed far more power and required extensive maintenance. American intelligence estimates from 1965 indicated that Soviet SS-7 and SS-8 missiles had guidance accuracy roughly 5 times worse than Minuteman, entirely because the Soviet semiconductor industry had not mastered silicon transistor manufacturing at the scale and reliability the Americans had achieved. The strategic implications were profound. Accurate guidance meant the United States could target Soviet missile silos, command bunkers, and military installations with confidence that warheads would destroy their intended targets. Soviet missiles were only accurate enough for city targeting, massive destruction of population centers, but limited capability against hardened military targets. This accuracy advantage gave American strategic planners options in nuclear war scenarios that Soviet planners lacked, and both sides knew it. The silicon transistors that enabled this advantage had emerged from a basement argument at Shockley Semiconductor, been developed by an engineer who'd been fired for insisting that silicon was the future, and been refined through a manufacturing process designed to solve contamination problems. Now, they were deployed in 800 missiles, each containing guidance computers more powerful than anything that existed during World War II. The Minuteman production contracts transformed Fairchild Semiconductor from a startup with 30 employees in 1959 to a company with 12,000 workers by 1965. The Mountain View facility expanded across 40 acres, with clean rooms occupying 200,000 square feet and silicon crystal. Growing furnaces running continuously, monthly transistor production reached 2 million units, and the military contracts had proven that silicon manufacturing could scale from laboratory batches to industrial volume while maintaining the reliability that weapon systems demanded. But the real revolution was happening in the circuits themselves. Robert Noyce's insight about connecting multiple transistors on a single silicon chip had evolved from concept to production reality. By 1963, Fairchild was manufacturing integrated circuits containing 8 transistors, 16 resistors, and all the interconnections between them, entire logic gates fabricated as single units. The planar process made this possible because every component sat on a flat oxidized surface where photolithography could define patterns with precision measured in microns. Texas Instruments was pursuing integrated circuits simultaneously, and Jack Kilby had demonstrated the concept using germanium in 1958. But Kilby's approach required individual wire bonds connecting components, a technique that couldn't scale to complex circuits. Noyce's planar integrated circuits used deposited aluminum metallization to create connections, enabling circuits with hundreds of components that could be manufactured with the same photolithographic steps that defined the transistors themselves. The commercial implications extended far beyond military contracts. IBM announced the System 360 computer in April 1964, and the architecture depended entirely on integrated circuits for logic and memory. Each computer used thousands of chips containing multiple transistors, replacing the discrete component boards that had characterized earlier designs. The performance improvement was dramatic. Calculations per second increased tenfold, while power consumption dropped by similar factors. By 1966, IBM was purchasing integrated circuits at rates that exceeded military procurement. The semiconductor industry consolidated around silicon, and companies that had invested in germanium expertise found themselves obsolete. Germanium transistor production peaked in 1964 at 50 million units, then began declining as silicon devices became cost competitive even for consumer applications. By 1968, silicon transistor production exceeded 500 million units annually, and integrated circuits accounted for 30% of that volume. The transition from germanium to silicon that military requirements had forced was now complete across the entire electronics industry. Moore's law emerged from this production explosion. Gordon Moore, who had left Shockley alongside Hoerni and Noyce, published an observation in 1965 that the number of transistors on integrated circuits was doubling every year. He predicted this trend would continue, and it did, driven by improvements in photolithography that could define ever smaller features, by advances in crystal growing that produced larger silicon wafers, and by the planar process that made it possible to manufacture complex circuits with reasonable yields. The Defense Department applications multiplied. The Apollo guidance computer that would land astronauts on the moon used integrated circuits from Fairchild, 5600 NOR gates, fabricated as dual 3-input circuits on silicon chips. The F-111 fighter bomber's terrain-following radar used silicon transistors that processed returns fast enough to fly at 600 miles per hour, just 200 feet above ground. The BMEW's ballistic missile early warning system radar in Alaska used silicon amplifiers that could track incoming warheads while distinguishing them from decoys and debris. Soviet attempts to copy American integrated circuits through the 1960s failed consistently because they lacked the manufacturing infrastructure. Producing silicon transistors required cleanroom facilities, photolithography equipment, high-temperature furnaces, and quality control procedures that the Soviets could not replicate at scale. By 1970, the technology gap had widened to the point where American weapon systems operated with electronic capabilities that Soviet engineers understood theoretically, but could not implement practically. The strategic balance by 1970 revealed itself in numbers that Soviet military planners found increasingly alarming. American Minuteman III missiles achieved circular error, probable of 600 feet after refinements to the guidance computers, accurate enough to destroy hardened missile silos with high probability using single warheads. Soviet SS-9 missiles, the largest in their arsenal, could manage accuracy of only 1.5 miles despite carrying 25 megaton warheads. The difference wasn't nuclear physics or rocket propulsion. It was silicon transistors processing guidance calculations at speeds and with reliability that Soviet vacuum tube systems couldn't match. KH-9 hexagon spy satellites launched starting in 1971 carried cameras that could photograph objects 4 inches across from orbital altitude of 90 miles. The camera systems used silicon integrated circuits to control film advance, aperture settings, and exposure timing synchronized to satellite position and ground speed. Each satellite returned 60 miles of film, containing images covering 370,000 square miles of Soviet territory per mission. Photo interpreters could read license plates, identify aircraft types on airfields, and measure the dimensions of missiles on rail cars. Soviet satellite reconnaissance systems using tube-based electronics achieved resolution measured in feet, not inches. The accuracy gap extended to naval systems. The AN/BQQ-5 sonar installed on Los Angeles-class submarines beginning in 1972 used silicon signal processors that could simultaneously track 200 targets while distinguishing submarines from surface ships, whales, and underwater geological features. The system processed acoustic returns through Fourier transforms calculated in real time by integrated circuits, mathematical operations that would have required room-sized computers a decade earlier. Soviet submarines relied on analog processing that could track perhaps 20 targets with far less discrimination capability. American fighter aircraft carried radar systems like the AN/APG E-63 that used silicon-integrated circuits to track 10 targets simultaneously while guiding missiles to 4 of them. The radar could distinguish aircraft from ground clutter, identify friend or foe electronically, and calculate intercept solutions automatically. Soviet MiG-21 and MiG-23 fighters used vacuum tube radar systems that could track one target at a time and required pilots to calculate intercept geometry manually using instruments and training. By 1970, worldwide silicon transistor production exceeded 3 billion units annually, and the United States manufactured 65% of that total. Integrated circuit production reached 300 million units, with American companies dominating despite competition from Japanese firms that were beginning to master the manufacturing processes. The silicon transistors that Gene Hoerni had developed to solve reliability problems now cost less than germanium transistors had in 1960, while offering performance that germanium could never achieve. The economic transformation paralleled the military advantage. Silicon Valley, named for the element that made it possible, employed 80,000 workers in semiconductor manufacturing and related industries by 1970. Intel, founded by Noyce and Moore in 1968, introduced the 1103 dynamic RAM chip in 1970, storing 1024 bits on a single integrated circuit. This was the beginning of semiconductor memory that would replace magnetic cores in computers, enabling dramatic size and cost reductions. The Cold War would continue for another 2 decades, but the technological trajectory was established by 1970. American weapon systems operated with electronic sophistication that Soviet systems could not match because the United States had mastered silicon transistor manufacturing at scale. The basement argument at Shockley Semiconductor in 1958, where an engineer insisted that silicon was the future and got fired for it, had ultimately determined which superpower would maintain strategic superiority. Gene Hoerni's planar process, developed to prevent contamination of silicon junctions, had become the foundation of an industry producing billions of transistors annually. The man who'd been dismissed for refusing to work on germanium had solved the manufacturing challenge that made American technological dominance possible. William Shockley, who'd fired him, never produced a commercially successful semiconductor product.